Hello everyone. Today we are going to see what is efficiency. Efficiency. Suppose we have two unbiased estimator T1 and T2. If we have two unbiased estimator, then there will be infinitely many unbiased estimator we can construct, like alpha T1 plus 1 minus alpha T2. Alpha belongs to 0 to 1. So here we can construct infinitely many unbiased estimators. So question remains, which unbiased estimator is good than other? So in this case, efficiency of estimator is C. So what is efficiency? Efficiency is nothing but variation of unbiased estimator around T. Means expected value of T1 minus expected value of T1 bracket square, but T1 is unbiased, so expected value of T1 minus theta bracket square. So it is a variance. So if variation of unbiased estimator around theta is minimum, then we will call it as efficient estimator than other estimators. So suppose this is a distribution of T1 and this is a distribution of sampling distribution of T2 and this is a theta. So here variation of theta for T2 is considerably minimum than variation of theta along T1. So here we can see that variation of T2 from theta is minimum than T1. So here T1 is efficient. So how we define efficiency? Before define efficiency, we have to define precision. Precision means 1 upon variance of that estimator is called as a precision. So efficiency of T1 given T2 is 1 upon variance of T1 divided by 1 upon variance of T2. So that is efficiency, precision of T1, and this is precision of T2. So what we have, variance of T2 divided by variance of T1. If this ratio is greater than 1, if this ratio is efficiency is greater than 1, then T1 is efficient. If E is less than 1, if E is less than 1, so here T1 is not efficient as compared to T2. And if it is equal to 1, then T1 and T2 both are equally efficient. So these are the interpretation for efficiency. If E is greater than 1, if E is greater than 1, it means this value is greater than this value. So here T1 is efficient. If this value is efficiency is less than 1, then it means that this value is less than this value. So T1 is not efficient than T2, and if equal to 1, then both are efficient, equally efficient. So next we will see some examples for efficiency. Suppose we have a random sample x1, x2, x4 from Python lambda. Then we have to check t is equal to x1 plus 2x2 plus x3, 3x3 plus 4x4 divided by 10 is efficient or not, is efficient or not than x bar, which is equal to x1 plus x2 plus x3 plus x4 divided by 4. To solve such examples, we have to know some basic results of variance and expectation. we have to know that expected value of ax plus by is equal to a into expected value of x plus b into expected value of y, where a and b are constant, real numbers. And variance of ax plus by is equal to a square into variance of x plus b square into variance of y plus 2 times covariance of xy. If x and y are correlated, if they are not, if they are independent, then covariance becomes 0. In this case, a square variance of x plus b square variance of y, if they are independent. Similarly, in case of minus sign, we have to replace minus sign here only for covariance and expectation. So, like this, we can find variance and expectations. So, now we consider t is equal to x1 plus 2x2 plus 3x3 plus 4x4. So expected value of t is equal to expected value of x1 plus 2x2 plus 3x3 plus 4x4 divided by 10. So what we have? We have taken 1 upon 10 is constant, so we can take it outside the expectation. And expectation of x1 plus 2 into expectation of x2 plus 3 into expectation of x3 plus 4 into expectation of x4. Now we can see that all expected values of xi is the same as Python, as xi's are belong from Python lambda. So all expectations of xi is lambda. So it becomes lambda plus 2 lambda plus 3 lambda plus 4 lambda, and this is equal to 10 lambda divided by 10, and it is equal to lambda. So we have proved that first t is unbiased estimator of lambda. So now we calculate variance of t. Variance of t is equal to variance of x1 plus x2 plus 2x2 plus 3x3 plus 4x4 divided by 10. So now what we have? 1 upon 10 comes out from the variance as it is constant, and it comes at 1 upon 10 square into variance of x1 plus variance of x2 can be written as 2 square into variance of x2 plus 3 square into variance of x3 plus 4 square into variance of x4. So what we have? 1 upon 10 square. Variance of x1 is lambda. As it is Poisson distribution, mean and variance is same lambda. So lambda plus 4 lambda plus 9 lambda plus 16 lambda. So what we have? 1 upon 10 square, it is 100. So 16 plus 9, 25, and 5, 30. 30 lambda. So 3 upon 10 into lambda, which is a variance of t. Now we will go for x bar. 3 upon 10 lambda. Variance of t, 3 by 10 into lambda we have. So as we know, sample mean is unbiased estimator of population mean. Sample mean is unbiased estimator of a population mean. So expected value of x bar comes out to be lambda, as it is unbiased estimator of population mean, and population belongs to Poisson distribution. So variance of x bar is equal to variance of x1 plus x2 plus x3 plus x4 divided by 4, and 1 upon 4 comes at 1 upon 4 square. Variance of x1 plus variance of x2 plus variance of x3 plus variance of x4. Now we can see that x1, x2, x4, x3, x4 are random sample from Poisson lambda. So these variances comes in addition, and covariance term is vanishes because they are random sample and they are independent. So 1 upon 4 square into 4 lambda, it is equal to lambda by 4. So variance of x bar is lambda by 4. Now we will go to calculate efficiency. Efficiency of T1 given T2 is defined as variance of T2 divided by variance of T1. So here we have to calculate for here our T1 is x1 plus 2x2 plus 3x4 plus 3x3 plus 4x4 divided by 10, and T2 is x bar and T2 is x bar. So what we have, variance of T2 is lambda by 4 and this is 10 by 10 into lambda. So what we have, lambda gets cancelled, 10 divided by 12, and which is less than 1, which is less than 1. So T1 is not efficient than T2 is not efficient than T2. So here T2 is efficient. T2 is efficient, that is x bar is efficient estimator than T1. So this is first example. Now we can take same example from normal mu sigma square. Suppose we have 3 random sample from normal mu sigma square. So if we have T1 x1 plus 2x2 plus 3x3 divided by 6, then expected value of T1 is 1 by 6, expectation of x1 plus 2 into expected value of x2 plus 3 into expected value of x3. So what we have, 1 upon 6, and this is mu plus 2 mu plus 3 mu, and 6 mu upon 6 is equal to mu. So T1 is unbiased estimator of mu, and suppose T2 is mean. So we know that sample mean is unbiased estimator of population mean. So expected value of T2 is also mean. Now we will calculate variance of T1 and T2. So variance of T1 is equal to variance of this term, and in variance term 1 upon 6 come out from variance as 1 upon 6 square into variance of x1 plus 2 square into variance of x2 plus 3 square into variance of x3. So 1 upon 36 sigma square plus 4 sigma square plus 9 sigma square, and which is comes out to be 14 sigma square by 36, and which is equal to 7 by 12 sigma square. And we know that variance of x bar can be calculated as variance of x bar is equal to 1 upon 3 square into variance of x1 plus variance of x2 plus variance of x3, and which is equal to 3 sigma square divided by sigma square, 3 square. So what we have, sigma square by 3. Now we calculate efficiency of T1 with respect to T2. So what we have, variance of T2 divided by variance of T1, and which is equal to variance of T2, what we have, 7 by 12 sigma square divided by sigma square by 3. So it becomes 21 by 12 sigma square, which is greater than 1. Now sigma square is cancelled. 21 by 12 greater than 1. So here T2 is not efficient, so T1 is efficient than T2. So T1 is not efficient. That is T2 is efficient. That is mean is efficient in this case. So Now we will move to another example. So our next example is